Assalamu alaikum. I'm Vivian Shwaikani. I will be explaining you the part 4 of the same chapter 5, strong acids and strong bases. Let's start by the objectives. In this chapter, we have 4 objectives to be covered. As usual, I will not read them. We will talk about each of them in this slide. Now, you need also to prepare the same materials as usual. Let's start by our first idea, which is about titration. Actually, titration is not a new idea. You saw it last year when we studied titration in a redox reaction, and you saw it also this year when you studied kinetic. Now, what about titration reaction? For the pH metric titration between an acid and a base, it is simply an experimental technique that allows to determine the concentration of unknown solution of an acid or a base. Now, the titration is based on a principle that it has to use a chemical reaction, or it has to be based upon a chemical reaction that must satisfy 3 characteristics. The reaction of titration has to be very rapid, it has to be complete, it's not reversible, it is complete, and it has to be unique. Other than if one of these characteristics is not present, the reaction cannot be used in titration. Now, about acid-base titration in this year, we have to talk only about the case of strong acid and strong base. This titration is based upon a reaction between a strong acid and a strong base that is called neutralization. Look how to represent the overall equation of this reaction. This is the H3O plus ion coming from the acid, and this is the hydroxide ion coming from the base. When they are put together, they react in order to give 2 water molecules. And you know that water is a neutral. This is why this reaction is called neutralization. One more thing to be added here, that in this lesson we will talk about something called the spectator ions. What is spectator ions? They are also called indifferent. Why? Because the acid here, for example, is HCl. We don't put H3O plus in a beaker, we put HCl. So the Cl minus that is split from H3O plus will stay in the beaker, but it doesn't interfere in the reaction. This is why we call it spectator or indifferent. Same of Na plus, for example, that is attached to NaOH in the sodium hydroxide base. Also Na plus will stay in the beaker, but it has nothing to do with the titration reaction. This is why it is an indifferent ion, and we will not represent it in the overall equation of the titration reaction. Now, what about the materials of the acid-base titration? Those materials also has to be memorized by heart. As any titration, the titration requires definitely a graduated burette, a stand, a beaker, a magnetic stirrer with its magnetic bar, and a pH meter, and this is a material specific for acid-base titration, while other materials are used for all kinds of titration. Now let's see the experimental setup in a schematic way of the acid-base titration. Look, we need the stand. As you can see, the stand here has 2 clamps. One of them is used to attach the graduated burette. In the burette, we put usually the solution of known concentration. It can be either acid or a base, it depends on the situation. Here in the beaker, we put the solution called analyte. You're not responsible after all for this word, but the analyte solution, it means the solution of unknown concentration. And we have to use, this is the magnetic stirrer. The stirrer is simply a machine that allows this magnetic bar to rotate inside the solution and to mix it. So its role is simply to mix what is in the beaker. And finally, we have the pH meter. That is an instrument, a digital instrument. It has an electrode here, a sensitive electrode. Once the electrode is in the beaker, it allows this machine to show us the pH value at each time in the beaker. So this is about the experimental setup. Now, what is the experimental principle of acid-base titration? An acid-base titration, or the values of the pH recorded by the pH meter, consists to following the pH evolution or the pH change in the beaker It means of the solution of the unknown concentration. And these values definitely upon adding the titrant solution that is in the beaker, in the burette. Now the different values of pH obtained will allow us to draw something called the pH metric titration curve, because we collect many values of pH. As we said here, the different values of the measured pH after each addition of the solution that is in the burette allows us to draw a curve that is pH equal function V titrant solution. What does that mean? You don't have to memorize this form. I know it's not nice for students. It's simply a curve of pH as a function of the volume added from the burette. Now, if the acid solution is in the burette, the curve will be descending. If the basic solution is in the burette, the curve will be ascending. About this idea, you will understand it in the coming slides. Here is a video that will show us the experimental principle and how to draw the curve of the acid-base titration. So look, this is the setup of the titration reaction. Here we have the base is in the burette and the acid is in the beaker. Look, we have started to add 1 drop, let's say, or 1 milliliter of the NaOH solution, which is a base over an acid. Now, the initial pH here would be less than 7 because here is an acidic, there is an acid in the beaker. So let's wait to show the curve. Okay, so can you see? This is the curve. Here it is pH on the y-axis and here the volume of the base added. As you can see, this yellow, it's about the dots or the points of the pH read here by the pH metric. So as long as we add, as you can see here, there is a decrease in the volume. It means the base is added. Look, the pH in the beaker is going to change, allowing us to draw what? To draw this curve. Notice here something very important. After this point, directly the value of the pH recorded is here. So there is nothing here between those. But we can, using a pencil, we can relate these two parts of the curve. So this is how to obtain the curve based on the value read by the pH meter. Now, let's study the curve of HCl solution by NaOH solution, the titration curve. Look here. It is a curve showing pH at the y-axis and showing the volume of the sodium hydroxide solution. It means of the base added. At the beginning here, the pH is less than 7 and then it's increasing. So the curve is ascending because the acid is in the beaker. In this case, as we said, the base NaOH is in the burette and the acid HCl in the beaker, exactly as in the video shown in the previous slide. After each addition of a certain volume of NaOH, for example, after the addition of 1 milliliter, we record the pH value measured by the pH meter. And we draw the curve that is called pH function of what? Of VB, as you can see here. Now, the pH initial, as you can see here, it is less than 7, simply because the acid is in the beaker. The pH increases upon titration, as you can see, because the base is added to the beaker. So the curve is ascending. Now, also, let's analyze in details the shape of the titration curve of the acid by a base. As you can see, what do we have here? We have a curve that consists of 3 parts, the red, the blue, and the green. And it has an inflection point that is here. You know in math what is an inflection point. Let's start by the first part. The first part that is in red, AB. It makes what do we call a plateau. Plateau is simply a French word that means almost a horizontal line. Why? Because the pH here varies really slightly. Now the second part, BC, here as you can see, the curve shows what do we call a sudden jump of the pH. It means in just the addition of one drop of base, the pH, for example, varies of a value that is, I don't know, 3 maybe, to become directly 7. This is what do we call a jump. And this part, which is the jump, where the variation of the pH occurs, contains what do we call E, the inflection point. And finally, we have the third part that is drawn here by green, CD. The pH varies slightly and makes again what do we call a plateau. And the curve tends to what do we call a horizontal asymptote. Again, related to the curve. Pay attention here to point A. At point A here, we have no base added. Simply we have the acidic solution, initial one. So the pH at point A can be calculated applying this formula, minus log concentration of H3O+, and H3O+ is equal to the concentration of the acid solution. Now, the point E is called the equivalence point, where the reactants react according to their stoichiometric proportions. It means at E, we have no more acid, no more base, because the acid existing in the beaker reacts with the base added from the burette with the equal amount to their stoichiometric coefficient. So the pH is neutral, is 7. The coordinates, so of point A, E, it's the abscissa here, is the volume of the base added at this point, and the ordinate here is the pH, which is usually 7 in our case. Now at point D, at D here we don't have any more acid. Acid has finished here. So here just we have the base that is increasing. So the pH can be calculated by applying the formula 14 plus log of the concentration of OH minus, where OH minus is the concentration of this ion in the beaker at the end of titration. Now, the equivalence point E shown there can be determined graphically. How? We can determine it graphically by applying a method called the method of the parallel tangents. How is this method applied? This is the curve. We have to trace here a tangent after the variation of the pH and before the variation of the pH, but these two tangents drawn here in blue has to be parallel. And then we have to draw a third line here that is green at an equidistant that is equidistant to two tangent, and this line cuts the curve at a point called E. I know I have explained it quickly, but now I will show you a video in order to know how to determine graphically the equivalence point E. Look at this curve. This is an acid is in the beaker and the base is in the burette. This is the first tangent. Can you see it using a ruler? Then this is the second tangent, and we use the set square in order to be sure that both tangents are parallel. And this is the line that is equidistant of both tangents. This line, look, it cuts the curve, can you see, at a point called E, the equivalence point. This is X, VE, the abscissa of E, and this is Y. Now let's consider the other way around. It means the base is in the beaker and the acid is in the burette. In the same way, the first tangent, the second parallel tangent, and then, yes, the line that is equidistant of both tangents. And as you can see, this line cuts the curve with the equivalent point E, having an abscissa VE and an ordinate pH equivalence. So this is how to determine graphically the equivalence point E. Now our lesson ends, so please read carefully what is required from you in the agenda, where you have to draw or to study by heart the characteristics of the titration reaction, and you have to memorize the materials, you have to draw the schema of the titration setup, and you have to memorize the shapes of the curve. Thank you for your attention.